All right, so now we're going to go through how to calculate a confidence interval and also where this comes from and how it works. All right, so I'm going to carry on with the example that we had in the slides. So we sampled 100 people. And we asked them, how do you think different crimes should be sentenced? So what punishment do you think is appropriate for different crimes, such as robbery? And in our sample of 100 people, the mean preferred sentence for robbery was 10.6 years. So when you see sample of some number of people, that's always your n, and then when we're referring to a sample mean, we're going to call that x bar. And what we're going to do is we're going to find a 90% confidence interval. So we want to find a buffer around this point estimate, so some interval or range of values that is 90% likely to include the true preferred sentence for robbery among people in the United States. So essentially what we're doing is we have our point estimate here, and we want to find, some range of values. We don't know what they are yet, but that's 90% likely to include the population mean. And remember, we're not saying that there's a 90% chance that the population mean is going to be within whatever interval we calculate. We're going to be saying that our interval has a 90% chance of landing on top of the population mean. All right, so here's where we're going to go back to what we talked about in the last week before spring break. So in the last week before spring break, as I said we were going to be applying it, so here we are applying it. We learned about sampling distributions, where we have our sample means down here, and the probability of getting each one. And we said that when we have a sample of 30 or more, our sampling distribution is going to be normally distributed like this. So it's going to have an overall mean of sample means and then some standard deviation for sample means. So this here is just a normal sampling distribution. And we know that this is going to describe the different possible sample means that we could get when we take a sample of 100 people, because it's a pretty large sample. So in other words, whatever the true population mean is, we're most likely to have a sample mean that's close to it. We're less likely to have a sample mean that's really far away from it. Right, so we have our higher hump here. These are our more likely sample means. And then as you go further out, it gets less and less likely that you'll get a sample mean that's much bigger than our true population mean or much smaller than our true population mean. But the issue here is that we don't know what this actually is. Right? So we don't know the true population mean, and that's what we're trying to estimate using our sample. But what we can do is say that, knowing that this is what the distribution is like, we can use our sample mean as a best guess for what that true population mean is. And we'll still have information about, how far out different sample means are likely to be, and how they're distributed around what our best guess for the true population mean is. And so essentially what we're trying to do here is we've got x bar, so these are our sample means again. This is our best guess for the true population mean, which we're using, or which we got by taking a sample and using our sample mean as a point estimate or a best guess for what the true population mean is. What we want to do is find an interval around our best guess of 10.6 that has a 90% chance of landing on top of the true population mean. So what we do here is we use the properties of the sampling distribution to find an interval of values that is 90% likely to include the true population mean. And we do this by thinking about the sampling distribution, where we have the different sample means you can get at the bottom and the probability of getting each one. We also know that the area under the curve in a sampling distribution tells us the probability of getting an outcome in between two values. In the last couple of classes, we've been using probability distributions and sampling distributions to start with values on the bottom and then find the probability of getting some value between them. All we're doing here is flipping that around. So instead of saying what's the probability of getting a sample with a mean between, say, 10 and 12 years, instead we are now saying we have our best guess for the true population mean at 10.6, and what range of values, includes a 90% chance of getting that outcome. So similar to what we did last week, except instead of finding this probability, we're now finding the values that include a specific probability. And what these values will correspond to is this buffer zone that we want to find around x. So we've got x down here, we've got our values here, and we're using the normal distribution to fill them in. So again, using the properties of this normal sampling distribution, we're going to be able to find an interval that we can be 90% confident includes the true population mean, using our point estimate as our best guess, and the fact that the area under the curve corresponds to the probability of getting an outcome within some range of values. And before I move on, I'm going to quickly explain where that table of different critical z-scores came from. So when we're working with a normal distribution, we can always turn it into a standard normal distribution that has z-scores on the bottom. So we can convert our normal distribution into a standard normal distribution by converting everything to z-scores. So like I like to say, this is like going from feet to inches. The only thing we're changing are the units that we're counting in. So instead of counting in years like we are here with a mean of 10.6, now we're counting in z-scores. So of course we have a mean of 0, and we also have a standard deviation of 1. We can take what we drew here and put it into our standard normal distribution graph here. So we're still interested in the values that bracket 90% of the area under the curve. Except now we're counting in z-scores. So you may be guessing where I'm going with this, but the z-scores that correspond to these question marks are your critical z-values. So when you have a standard normal distribution, you know the values that are going to give you an interval that includes 90% of the area under the curve. And they're going to be the same values each time because the standard normal distribution is always the same each time. It has the same properties every single time once you convert your raw scores to z-scores. So the same two values will always bracket 90% of the area under the curve, just like the same two values will always bracket 95% and 99% of the area under the curve. So I'm just going to draw these out real small here. So this is where your critical z-values come from, and these are the z-values that are listed in that table. If you have a 90% confidence interval, we're looking at the z-scores on either side of 90% of the area under the curve, and the z-scores are always going to be 1.645 and negative 1.645. If you're looking at a 95% confidence interval, you're interested in the z-scores that bracket 95% of the area under the curve. And these are always going to be 1.96 and negative 1.96. If you're interested in a 99% confidence interval, and again, these are chosen by the researcher just based on how much confidence you want to have, how narrow or wide you want your interval to be. So if you're looking at a 99% confidence interval, you're interested in the z-scores that bracket 99% of the area under the curve. And these come out to 2.58 and negative 2.58. So to sum up here, what we're interested in finding with the confidence interval is this range of values around our sample mean that most likely includes the population mean at some level of confidence. And we find the range of values by using the normal distribution that describes the sample means that you're likely to get when you take a large sample. So we're interested in finding an interval that we can be 90% confident includes the true population mean. We're going to get our 90% confidence by converting everything to a standard normal distribution and figuring out which z-scores include 90% of the area under the curve. And we're going to be using those to calculate our range of values and fill in these question marks that we have here. So these are your critical z-scores, and that's what they are and where they come from. And as I sometimes do here, I like to go through piece by piece and show where the different parts of the equation come from and describe what they are. But after this, I'll also go through an example where I'll just plug in some numbers and you can kind of see what you have to do without all of this additional explanation. But if you remember on the last slide, we had two steps to finding our confidence interval. So our first one was find the critical z-score. And the second one was to use the confidence interval formula. So on this page, I described what the confidence interval is a little bit, but then I mostly have focused on finding that critical z-score. So the critical z-score are the z-values that include whatever area under the curve you are interested in based on your confidence level. So if you have a 90% confidence interval, you know for sure that your critical z-values are always going to be plus or minus 1.645. And that's based on the fact that we're working with the standard normal distribution, so the z-scores on either side of some amount of area under the curve are totally standardized. They're the same each time because the standard normal distribution is the same each time. Alright, so this is just step one here, finding the critical z-score. Now we're going to go into the confidence interval formula itself and how to calculate it. So your confidence interval formula looks like this, where x bar is your sample mean, z is your critical z value, for your critical z-score. And again, that's totally based on what your confidence level is. So if it's 90%, it's going to be plus or minus 1.645. If it's 95%, it's going to be plus or minus 1.96. If it's 99%, it's going to be plus or minus 2.58. So that's your critical z-score. Sigma means also what it usually does in statistics, and that's your population standard deviation. And finally, n also has its usual meaning, and that's the sample size. Alright, so let's think about what we know so far. We have a sample of 100 people, so that's n. We have a sample mean of 10.6 years, that's x bar. We have a critical z of plus or minus 1.645. So that's z in this equation. Alright, so we have x bar, we have z, and we have n. But what about the population standard deviation? Alright, so what the population standard deviation refers to here would be the standard deviation for the variable preferred number of years for a robbery sentence in the United States population as a whole. So you may notice that we have a bit of a conundrum here. We're trying to use this formula to estimate the true mean value, but the formula requires us to know the true standard deviation value. And that's just not that plausible, right? There aren't that many situations where you know the standard deviation for the population, but you don't know the mean value. And so you probably don't know the population standard deviation. And there will be some exceptions to this. And exceptions to this rule would include things like IQ tests or other standardized tests, where things like the standard deviation are set by the people who make the test, and it's known, and it's just sort of adjusted and finagled, and so there isn't really a population value to know other than what's already set and established. So in an IQ test, and I'm going to kick myself if these are the wrong numbers, but pretty sure these are the right numbers. IQ tests are set so that no matter what, the mean value is always 100 and the standard deviation is always 15. So if you were doing some sort of problem and you were trying to find a confidence interval for an IQ test, you would know the population standard deviation because it would be set by the people who make the IQ test. And in that case, you would just plug it in, you'd be good to go here. And so if you ever do know the population standard deviation, you want to use it because that's going to give you the best estimate. But most of the time, you're just not going to know it. So what we do instead is we estimate it using our sample. And so the actual confidence interval formula that we're going to use in this class is going to be one that uses an estimate of the standard deviation. So this one here, I'm going to say this is for known standard deviation, or sigma. But the confidence interval that's more commonly used, and the one that I'm going to mostly have you guys be taking a look at this week, is a confidence interval where the population standard deviation is not known. The reason that I show you this one first, though, is that everything we did here is based on the idea that we know the population standard deviation, because we can't come up with a standard normal distribution unless we know the population standard deviation. So your best estimates and the basis for what we're doing come from a world in which you know the population standard deviation, like you would if you were doing something with scores from an IQ test. So that's why I show you that one first, even though it's rarely used in practice because, like I said, you probably don't know this value. But what we use instead is going to be a confidence interval formula with an estimated standard error. So I'll now talk about what all this means. X bar is our sample mean as usual. Z is our critical z-score. S, so we've replaced sigma with S. S is also going to mean what it usually does, which is the sample standard deviation. And then N is our sample size again. And this is for situations where you don't know the standard deviation in the population. And again, the more likely situation than the first one, with the exception of times when, for whatever reason, there is some sort of standardized or known population standard deviation. Okay, so we're going to go right back in now, using the information that we have listed here. So we know the sample size, N, we know the sample mean, X bar, and we have our critical z-score picked out based on our confidence level. So we're looking at a 90% confidence interval. The only thing that we need to add here is our sample standard deviation. And so, you're assuming you've collected data from these 100 people, you have scores on this variable. This is something that you can just calculate because your sample is right in front of you. So I'm going to add a value here for the sample standard deviation. And we're going to say that the standard deviation is 5.8 years. So in any of these problems, this is going to be given, but the idea being that you've collected your sample, it's 100 people, you found the sample mean, and you can find the sample standard deviation in the same way that you found the sample mean. So if you can find a sample mean, you can also find a sample standard deviation, because you're just calculating it from the data in your sample. So now we're at the point where we just plug things in. And so we're going to find our confidence interval. Using this equation, we have all the pieces that we need because we've got our estimated standard error in here. And I keep saying standard error, by the way, because if you remember, the SE, or the standard error, is calculated using the population standard deviation and the square root of n. Our estimated standard error, estimated SE, is going to be calculated using this little equation here, which is your sample standard deviation over the square root of n. Alright, so our confidence interval formula, finally, I'll stop going on and on about all this other stuff, is going to include our sample mean, which is 10.6 years, plus or minus our critical value of z, which is 1.645, and then divided by our sample standard deviation, or 5.8, over our square root of n, or square root of 100. And once we do this, we can just do our math here. So we get 10.6 plus or minus 1.645 times 0.58. So we're dividing by the square root of 100, which is 10. And then we get 10.6 plus or minus 0.95. Plus or minus, it just means that you're going to do two things here. So with one of them, you're going to add 0.95, and with one of them, you're going to subtract 0.95. And by doing that, we're going to get our interval. So when you subtract 0.95 from 10.6, you get 9.65. And when you add 0.95 to 10.6, you get 11.55. So what we've done here is we have filled in the range of values that is most likely to include our population mean. So this is 10.6 minus 0.95, and it comes out to 9.65. This is 10.6 plus 0.95, and this comes out to 11.55. And typically confidence intervals are reported like this, where you have one value, and then your lower value, and then a comma, and then your higher value. And that's describing this whole situation here where you have an interval that goes from 9.65 to 11.55 that most likely includes your true population mean. And the way we would describe this is that we would say we can be 90% confident that an interval from 9.65 to 11.55 includes the true population mean. So in the United States as a whole, we can be 90% confident that this range from 9.65 years to 11.5 years includes the true preferred sentence for robbery. Alright, so like I said, this was an example that also includes a whole lot of explanation and kind of what's going on step by step and how we get from one thing to another thing. So what I'm going to do now is just go through a much quicker example of how to use the confidence interval formula with the kind of data that you would most likely have. So for this example number 2, we're going to say we have a sample of 40 police officers. And I'll just put my... Oh, sorry. For whatever reason, I do pretty much the same notes every year, but I change them up slightly each time, thinking what works better, and somehow this time around I just have a giant pile of them that got all shuffled up while I was talking, so excuse me while I shuffle around. So in this example now we have a sample of 40 police officers, and we're looking at the number of arrests that each of them made in the past month. So we're going to say in this sample of 40 police officers, we have a mean of 16.3 arrests in the last month, and a standard deviation of 4.1 arrests. So we know going in that we're calculating a confidence interval, and so that means that we're going to need the sample mean and the sample standard deviation. So here we have our n, we have our x bar, and we have our s. Important thing to note about sample size, you can only use the estimated standard error equation when you have a sample size of 30 or greater. For the other one, it doesn't matter, but if you're estimating the standard error, you can only do it if you have a sample size of 30 or greater, and this has to do with being certain that the sampling distribution that you're going to use is normal. So what I'm going to do is I'm also going to write that on these notes for when I post them. So for this one, any sample size is okay. Hang on, no, any sample size. Okay, so any sample size is okay. You know, if you have a normally distributed variable, and for this one, your sample size must be greater than 30 no matter what kind of variable you have. So even if you have a normally distributed variable, which normally would give us a normal distribution, for this one your sample size has to be greater than 30 no matter what. And after I go through the next example, I'm going to talk briefly about what you would use if your sample size was less than 30. But luckily, in criminal justice kind of applications, that's rarely the case anyway. So for this one, just keep in mind that your sample size must be greater than 30. So for our second example here, and I said I wasn't going to go through and talk about more stuff, but I did. So for our second example here, we want to find a 95% confidence interval for the number of arrests made by police officers in this department that we took a sample from. So we have our 95% confidence interval. We know that the confidence interval formula looks like this. When we don't know the population standard deviation, which in this case we're assuming that if we don't know the true mean, we don't know the population standard deviation either. So we're going to be using the confidence interval formula that we use when we don't know the population standard deviation. So again, this is more realistic. This is typically what you'll end up using. So we have our confidence interval formula that looks like this. We have our mean, which is 16.3 arrests. We have our sample standard deviation, which is 4.1 arrests. We have our sample size, which is 40. And the last thing we need here is our critical value of z. The critical value of z, as you'll recall, is totally based on what the confidence interval is. And you can check the table that's in the slides. You can check the notes. But when you have a confidence level of 95%, you have a critical value of z of plus or minus 1.96. So all that's left to do is plug this stuff in. So our confidence interval for the true mean number of arrests made by police officers based on this sample of 40 is going to be based on 16.3 for x bar, plus or minus our critical value of z, which is 1.96. 96. I swear I'm not actually drunk when I do this. Okay, 1.96. Our sample standard deviation is 4.1, and our sample size is 40. So we're going to take the square root of 40. Now we can do this math. So we got 16.3 plus or minus 1.96 times 0.65. That's what you get if you take the square root of 40 and then divide it into 4.1. And then this comes out to 16.3 plus or minus 1.27. So this gives us the same kind of answer that we had before, where we have our best estimate here, which is our point estimate, which is 16.3. Now we're going to take 16.3 minus 1.27 for our low estimate, so 16.3 minus 1.27, which gives us 15.03. And then we have 16.3 plus 1.27 for our upper level of the our upper limit of the interval, which gives us 17.57. So here we'd say we have an interval that goes from 15.03 to 17.57, and again, that's how we would write that. And we'd say we can be 95% certain that an interval from 15.03 arrests to 17.57 arrests includes the true population mean. And again, that's using this formula here, which we use when we have a sample size that's greater than 30, and we know, or we don't know, the true population standard deviation. So we only know the sample standard deviation, or S. All right, so my last order of business in this lecture is just going to be to briefly talk about how you could calculate confidence intervals for smaller samples, but I'm not actually going to make you do it. But go back in anyway, because I'm going to talk about a concept that's going to be on the quiz, and that's going to come back later in the semester.